All right, welcome back. In this video, we're going to be talking about orthogonal spaces. And so if we've got two subspaces of Rn, we can say that they're orthogonal if every vector in each space is orthogonal to every vector in the other space. And so we say that v dot w equals 0 for all v in space v and all w in space w, then v and w are orthogonal subspaces. So I think I would draw you a couple of examples of ones that we can see in R2 and R3. So let's start with R2. In R2, really the only subspaces of R2 besides, the whole plane and just the zero vector are going to be lines that pass through the origin. And so our picture of orthogonal spaces are going to be lines that pass through the origin that are sitting orthogonal to one another. And I don't think it's that hard to envision, just looking at that every vector on V is orthogonal to every vector on W, right? They're meeting at a right angle, or at least close enough to be believable as a right angle. And so, if you think about any vector that starts at the origin and goes out the red line in either direction, and any vector that starts at the origin and goes out the blue line either direction, they're going to sit orthogonal to each other. Then in R3, we could also obviously have the lines that are sitting orthogonal to one another that are passing through the origin, but you don't need me to draw you the same picture twice, right? The other thing that can happen is we can have a line and a plane that are intersecting, at a right angle, that are, intersecting at that zero vector, at the origin. These will be orthogonal subspaces. And I think what I might draw on top of this a little bit for you, if we've got any old vector in W that starts at the origin and goes out that way, it's going to be orthogonal to any vector along V, right? That those two are going to be meeting at a right angle, provided that the vector, or that the line V is hitting W at a right angle, which I kind of presumed it was in the first place. Okay, so that's what it looks like to have orthogonal spaces. Okay, and now you may be sitting there thinking, okay, well, what about two planes in R3 that are meeting at a right angle, that are also happen to be, going through the origin? And I am saying that those cannot be orthogonal as subspaces in the sense of the definition I just wrote above. And the reason I would give for you is to consider this vector right here. Okay, so this one right here that I've kind of drawn in yellow. So I think what I would point out to you if I label the blue plane as V and the red plane as W is that X is not the zero vector, but X is in both V and W. Okay, so if V and W were going to be orthogonal to one another, then X would have to be orthogonal to itself. And as a non-zero vector, it's going to be very difficult for that to be the case, right? So I dot X with itself, and that's going to equal the length of X squared, and that's going to be exactly not zero, right? Because X is not the zero vector. So since X is not orthogonal to itself, and it is, an element of both, or it's, in V, and it's not orthogonal to every element of W, basically what I'm saying is V and W are not orthogonal subspaces. But two planes in R4 can be orthogonal. And so I think that kind of gives you kind of a hint towards some of the issues with the dimensionality with these orthogonal subspaces. If we let V be the set of all vectors that their third and fourth components are equal to 0 in R4, that's a plane, it's a two-dimensional subspace. And W be the set of all vectors in R4 where their first two components are 0. W is also a plane, it's a two-dimensional subspace of R4. And you can pretty clearly see that any element of V is going to be orthogonal to any element of W just because of the placement of the zeros. Okay, so I think that's all I've got to say about that for now. Now, to connect this back to what we've been talking about recently, the four fundamental subspaces, what we can say is that for any matrix A, the null space of A is going to be orthogonal to its row space, and the null space of its transpose is going to be orthogonal to its column space. If you think about it, this makes a lot of sense. If you think about like an actual null space vector multiplying against the rows and getting all zeros, right? We'd be orthogonal to all the rows. Okay, so we're going to be orthogonal to the row space. And, but I'm going to draw you a little picture of this that you frequently see in a lot of textbooks. Give a little bit of explanation. You see this, these like kind of spaces. They're orthogonal. It's like, okay, well, that's not very helpful. But to kind of give it some context, think about a matrix A, which is going to be an m by n matrix. And think about the associated linear transform, f of x equals a times x. Okay, f is going to map Rn back into Rm. We've learned about that in this class. So, to give this picture a little bit of meaning, maybe I look at it as like before and after, like the pre and post image. Okay, and what I can say is, okay, well, the null space, that's all the vectors that are getting mapped onto 0. So I could draw a little arrow like that, okay? And what, hopefully we're on our way to learning about is that the row space vectors of A are getting mapped into the column space. Okay. And kind of the associated equations I might show you for these would be, okay, for the null space, that would be AX equals the 0 vector. And then over here, this is just AX equaling B, where B is some non-zero vector. But it's going to be consistent. Okay, now I would probably also extend this diagram and say that the matrix A transpose defines a map from Rm to Rn, where the null space of A transpose is mapping back onto 0, and the vectors out of the column space of A, which is the row space of the transpose, are mapping into the row space of A, which is the column space of A transpose. And those associated equations right there. Okay, but I think that's more of just kind of a hint of the types of things that you might investigate if you keep going further into linear algebra. Let me tell you how to find the actual orthogonal complement of a subspace. All right, now when it comes to the orthogonal complement, this is the set of all vectors that are orthogonal to all of the vectors in your space. Kind of it's a subspace that's cooked up just to be, an orthogonal subspace. So I think the first thing I would tell you is that for any subspace W perp, that's kind of this perpendicular symbol, that's what we call that, W perp is going to be a subspace. And I will just kind of show you the proof real quick right here. There it is, but that's not really the focus of this video, is why W perp is a subspace. I want to show you how to compute it and, kind of what it all means. Okay, now, if we are asked to compute W perp for some given subspace W, we're going to use what we found out earlier, that the column space of a matrix is orthogonal to the null space of its transpose, or its left null space, and the row space is orthogonal to the null space. We're going to use that fact. So we're going to express our subspace W that we want to find the orthogonal complement of as the row or column space of some matrix, and then compute an appropriate null space. And I'll show you what I mean here in a second. And so I thought we'd do maybe 2 examples here. The first one's pretty easy, and I want to show you 3 different ways you can think about this one. So we've got the subspace W, which is the set of all x's in R3, such that x1 plus 3x2 minus 2x3, that's going to equal 0. Okay, so find a basis for W perp, the orthogonal complement to W. Okay, so the first perspective I see is thinking about it kind of just algebraically, the algebra perspective. You've got a linear equation in x, y, and z. That's going to be a plane in R3. Okay, so we've got the kind of the plane equation x plus 3y minus 2z equals 0. We know the normal to that plane is going to be 1, 3, negative 2, and well, that's the only kind of space that can be orthogonal to a plane in R3 is a line. And so that normal, that passes through the origin, that would be a good one. Okay, we could also kind of go from the basis perspective, kind of just grinding through, being like, okay, we'll just express W as the column space of some matrix, and then find the null space of its transpose. Okay, so and this is probably not the best way, but what we could do is we could say, all right, W, satisfies this equation. I'm going to solve for x1. So if I have x1 in terms of x2 and x3, that means x2 and x3 are free variables. So a basis for W would be negative 3, 1, 0, and 2, 0, 1. Now, so we could put those together into a matrix and be like, okay, well, W is the column space of A, and we know that something orthogonal to a column space is the null space of the transpose, the left null space. Okay, so we could transpose, augment with 0, row reduce. Okay, this thing's already kind of row reduced enough for me to write down my solutions. And that's telling me that x2 is going to equal 3 of x1, and x3 is going to equal negative 2 of x1. So that means x1 is the free variable, and that's going to give me that basis 1, 3, negative 2. Okay, so again, the same answer. But then I think the, best of all would be the W is already a null space, or W is a kernel perspective. I couldn't really fit in null space with the amount of space I had. Okay, so if you're already thinking about, okay, well, W is already the null space of some matrix, I went to write down the matrix I was thinking of it as the null space of, and I realized you, the viewer, you probably wouldn't like to have just what would that be, a 1 by 3 matrix? So I went ahead and put a second row of all zeros in there. I think there could be any number of rows of all zeros underneath, and W would still be the null space of that matrix. Okay, well, we know that the null space is orthogonal to the row space. Okay, and we also learned somewhat recently that, a way that we can obtain a basis for the row space is by taking the non-zero rows of that matrix in reduced echelon form. Well, that thing's already in reduced echelon form, so I know that a basis for W perp is going to be 1, 3, negative 2. Now, the last example I've got for you is, here's a matrix A. V is going to be the null space of A. W is V perp. What is the dimension of W? Okay. Well, if W is the orthogonal complement of V and V is a null space, then W is going to be a row space. And so if we think about the dimension of the row space, what is it that's going to have, I thought it's going to be the left null space has an interesting dimension. Okay, well, this isn't that interesting of a problem, but, it was one I found. So, all right, what is the dimension of W? Well, I'm going to say that I can see that the rank of A is 2. And if you just were okay with what I said, okay, well, the row space, it's the, number of linearly independent rows of A, and that's pretty clearly going to be 2, so I'm going to get 2. And if you're good with that, well then, yeah, you're probably done with this video, right? So the rank of A is equal to 2, and that means the nullity, I don't think that's what I needed, equals 4 minus 2, which is 2, maybe the wrong video for that. But if I was thinking about the rank of A and the nullity of A, why did I need that? Oh. I don't know where I was going with that, if I'm going to be honest. But I'm going to just say W equals the row space of A, a reduced to echelon form, and then the rank is, maybe the rank is 2. That was what I was going to go for. I don't know. Either way, dimension of W is going to equal 2, and I'm just going to kind of leave it at that. Okay, so that's going to be all for this video. Thanks for watching.